York City, received his bachelor's degree from Sonoma State University in California, completed a PhD in mathematics from the University of Iowa, and then had a postdoc position at Bowdoin College in Maine while participating in the combinatorics seminars at MIT in Massachusetts. He started his position here at UW-Eau Claire in 2013 and now holds the title of full professor. Congratulations, aBa. He and his colorful bicycle are very happy here, especially due to the students who bring him joy from teaching them in the classroom and conducting research with them at various places in Eau Claire. Dr. aBa's title is A Tantalizing Tale of Numerical Sequences. So please prepare to be tantalized. I want to just welcome our remote viewers and let them know that if they have questions, we will have time for questions, of course, after the talk. And if you have questions, please use the Q&A function either at the top or bottom of your screen for those questions. And aBa, when we have questions from the audience, if I could just ask you to please repeat the questions.
Sure, can do that.
For the benefit of our online viewers.
Can do that.
Join me in welcoming Dr. aBa.
All right. I'd like to thank the organizers, of course, for inviting me to give this talk here in my home institution. This is great. I've given talks at UWC, but in the math department, to the math department. And this is great to see a lot of non-math faces in the crowd here. This is awesome. So as Erica said, this title of the talk is A Tantalizing Tale of Numerical Sequences. This talk is about joint work I've done with some students here who graduated already, and current student here, and my external collaborator, Dr. Jürgen Spilker in Germany. So it's about 2 projects. So let us begin. Oh, there will be a quiz after the talk, so pay attention. Pen in hand would be good. Let's see, Sarah, you got that? So that's good. All right. Everybody else is memorizing? That's fine. Okay. So this quote I heard in Denver at the joint mathematics meeting in 2020, and it sparked a lot inside me. So learning new mathematics with students is one of the greatest personal benefits of undergraduate research. And I was thinking, at this school, UWC is uniquely aligned to give so much to students, not just in teaching, but in scholarship. And I really love that because I learned so much from my students. And I would like to talk about 2 projects where I learned so much. Okay, so first of all, the first research team, this is Miko Scott, that's myself, and that's Dan Geyer. Miko graduated in 2020. Dan Geyer is graduated 22. Miko Scott is currently in industry. Dan has decided to go get a PhD, so he's at UW Washington and he's entering his 2nd year. And well, no, still in his 1st year. I can't do the math. And this should look familiar. This was pre-COVID. This was the concert in the park. Actually, it has returned now, which is good. And this is us, as Erica said in the bio, that I like to do research all over, not just in doing a concert in the park, but also at this Irish restaurant. You might recognize Dooley's. And we also worked, of course, at ECDC, because that's a nice place, a little pricey. I always have to buy grub and stuff for my students, but you know, that's part of the funding. So if you look carefully, these are the proofs that I'm omitting from the talk of some of our main results. You can't see them, but they're in the paper, and I'll give links to the paper at the end of the talk. So first of all, who is Fibonacci? First of all, his name, there's no person who walked the earth called Fibonacci. He's Leonardo Bonacci of Pisa, and sometimes he goes by Leonardo Pisano. So what's up with the Fibonacci? Well, the name Fibonacci comes from the Latin Filius Bonacci, meaning son of Bonacci. His father's name is Guglielmo Bonaccio, and Bonacci is just the plural of Bonaccio. So Bonacci is regarded as the family's name, kind of the way in the US we say the Smiths for the family of Joe Smith, we pluralize. All right. So that's Fibonacci, but I will use the name Fibonacci for this whole talk. Okay, so rabbits that never die and constantly mate. So in his book, Liber Bocci, written in 1202, Fibonacci poses the following hypothetical, biologically unrealistic problem. A newly born pair of rabbits, one male, one female, are put in a field. How many pairs of rabbits can be produced from that pair in a year if the following holds? The rabbits live forever. When giving birth, a male and female pair will give birth to another male and female pair. Well, Well, I did say biologically unrealistic. No rabbits have any issues with inbreeding or incest. And this is the important one. Every month, each adult pair births a new young pair of rabbits, which from the second month on, second underlined, can themselves birth a young pair of rabbits. So let's construct the Fibonacci sequence visually. So beginning of the first month, we have Allie and Al are put into a field. So we have Fibonacci number one pair of rabbits. We're counting the pairs, not the number of rabbits, but the pairs of rabbits. And the beginning of the second month, Allie and Al are now full-grown adults and prepared to mate. So the second Fibonacci number is still 1 because we're counting the number of pairs of rabbits in the field. Beginning of the third month, Allie and Al give birth to Bella and Ben. So we have 2 pairs of rabbits, our third Fibonacci number. By the beginning of the fourth month, Allie and Al give birth to Cora and Cruz, while Bella and Ben become adults and prepared to mate. See how they've grown? They kind of look like mom and dad a bit, yeah? And so these are the new offspring of Allie and Al. So Fibonacci number 4 is 3. Beginning of the fifth month, Allie and Al give birth to Delia and Diego. Bella and Ben give birth to Ethan and Elijah. Cora and Cruz become adults and prepared to meet. Aren't they cute? The new ones? Yes. So the fifth Fibonacci number is 5. Beginning of the sixth month, Allie and Al give birth to Fran and Francois. Bella and Ben give birth to Gia and Gianni. Cora and Cruz give birth to Hadassah and Henri, while Delia and Diego and Edith and Elijah become adults and prepared to mate. The sixth one is the sixth Fibonacci number is 8. This is, by the way, the whole talk. I'm going to continue doing this for like until we. Okay, so Dr. Rabbit says, stop this sequence of silly rabbit news. Now we're going to get to some serious math. This is what the quiz is on. Okay, here are the first 30 positive Fibonacci numbers. And 233 is the number, the answer to the question about how many pairs of rabbits do we have in the field after 1 year has passed. That's the 13th Fibonacci number. Okay, so let's get to some more dedicated math. The Fibonacci sequence, denoted F sub n, and the Lucas sequence, denoted L sub n, are defined by the recurrence relation. The current term is the sum of the previous 2. So do we see that? 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, et cetera, et cetera, et cetera. The Lucas sequence is a related sequence. It has the same recurrence relation, but why does it not give the same exact sequence? Well, it has different starting values. The Fibonacci numbers start at 0 and 1. The Lucas sequence starts at 2 and 1. So we have the following Fibonacci numbers here. In the previous slide, I started with 1 as the first one. Technically, the very first Fibonacci number is the 0. 0, that's F sub 0. And the Lucas sequence goes like this. 2 plus 1 is 3, 1 plus 3 is 4, 3 plus 4 is 7, 4 plus 7 is 11, etc. And the Lucas sequence is named after Edward Lucas, who in the 1800s is basically the person who found Fibonacci and brought him to fame and was the first to use the term Fibonacci for the sequence. Lucas studied lots of relationships between the two sequences, the one by Fibonacci and the one authored by himself. For instance, in this visual image, we can see that if we add pairs of Fibonacci numbers that are 1 apart, 0 plus 1 is 1, 1 plus 2 is 3, 1 plus 3 is 4, 2 plus 5 is 7. We get the Lucas number right on in between them. And you would ask yourself, well, what happens if we add the Lucas numbers? Like 2 plus 3, that's not 5, that's 1. 1 plus 4, that's not 5, that's 1. 3 plus 7, that's not 5, that's 10. 10, that's not 10. But 4 plus 11, that's 15, but that 3 is not 15. Does anyone see a connection of how 3 is connected to 15, how 2 is connected to 10, how 1 is connected to 5? You do? Multiples of 5, yes. So we got 7 plus 18 is 25, that's 5 times 5. 11 times 29 is 40, that's 8 times 5. So there's a 5 connection here. Ironically, through the Lucas sequence, through the infinite number of terms, it's been proven that none will ever be divisible by 5. So this is a very 5-hating sequence, or 5 avoiding. But for a sequence that hates 5, the myriad connections between these two always involve the number 5, often. So it wants to hate it visually, but if you inspect it deeper, you expose the 5. And there's a really good mathematical reason for that too. And I'm not going to say why. Okay, so recall the Fibonacci sequence is above here, that list. Now we're going to define a new thing. The nth Fibonacci number modulo 10 is going to be denoted curly f 10 sub n, 10 comma n. And is defined to be f sub n modulo 10. I'm not going to give a lesson in modular arithmetic because the sequence mod 10 is simply taking the original sequence and looking at the last digit, the units digit. So for instance, we have 13 here is after the 8. Instead, after the 8, we have 3. We have 21 there. Instead, we have 1. We have 34 up here. Instead, we have 4. And also, this sequence, mod 10, does exhibit the Fibonacci recurrence also. 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13, but we only look at the last digit, so we get 3. 8 plus 3 is 11, so we have 1. 3 plus 1 is 4. 1 plus 4 is 5. 4 plus 5 is 9. 5 plus 9 is 14. Last digit, we get 4. And we can see how that's coming on. So it's a really easy sequence to look at modulo 10 in particular. So consider first 87 terms of this modulo 10 Fibonacci sequence. It starts with 0, 1, 1. Does this sequence repeat at some point? Does anyone see another 0, 1, 1? Does it repeat? I mean, there's a lot of numbers up here. I'll save your eyes. You're all in the back because I insisted you come to the front, but here you go. Right there, it starts repeating. Again, the exact same thing. So, and this is just me writing, again, it shows the Fibonacci-esque recurrence. We use this symbol that looks like equals to mean congruence, like the idea that 9 plus 1 is 10, but this sequence that says look at by the last digit modulo 10, we have the 0 there. So we can't put an equal symbol there. We do a congruent symbol. So what does sad dog say? It's a periodic sequence and has a period of length 60. Why is he sad? Because this is common knowledge. As far back as 1774, Lagrange declared that the Fibonacci sequence modulo 10 is periodic of length 60. Of course, he probably didn't say Fibonacci because it was still some 100 years before Edouard Lucas coined the term in popularity. But in 1960, in particular, a seminal paper by D.D. Wall brought this research into the modern world. This paper alone spawned a lot of mathematics on the Fibonacci, a resurgence on the Fibonacci sequence. So that begins our topic, our research on this topic at UWEC. So what if we place the 60 values on a circle like so? We start with the top one being the 0, 1, 1, and we spin around with all those 60 terms that's in a single period. So we have the value curly f10 comma I equals the value f10 comma I mod 60. What do I mean by that? This is the 0th term, curly f0, curly f1, but after 60 items, this is now curly f61, 62, 63, 64, and then after this is curly f120. So we have an infinite sequence, really. I mean, it repeats in blocks of 60, the exact same 60 terms, but it's we can shoot off to infinity. And in fact, we can shoot off to the left to negative infinity too, if we'd like, if we desire. Nothing is stopping us from doing that. So, you might also say, why did you put it around in a circle? Astrology. Aries. The zeros are at the cardinal signs. If you want to think about that, Aries, Cancer, Libra, Capricorn. Sorry, it's getting cold. I don't like saying the birth of winter signs. And at the 5s, we have the fixed signs, like this is Taurus, and mutable signs. I got this from a YouTube video. Which actually the YouTube video is 20 minutes long by a really famous astrologer named David Cochran, had all these amazing ideas on the mathematics of this, but he was an astrologer, not a mathematician. So when I watched the video, I was like, oh, this is so intriguing. And I showed it to my students, and I was like, let's look into this. But I try not to say the astrology word too much because then people are like, is this serious math? It definitely is. But was it birthed from astrology? It definitely was. Okay. All right. So subsequences of the form f curly f10 comma k plus r j going from 0 to infinity. Okay, that's a jumble. So let's give an example. Example will help. So let's set k to be 1, r to be 15, and then this sequence is essentially starting at the curly f1 and then jump sizes of 15. So we have curly f1, curly f16, curly f31, curly f46, 61, 76, et cetera, et cetera. These values are 1793, and it repeats 1793. And so if we look at it, a jump size of 15 on a circle that has 60 ticks, well, that would be 1/4 of the circle every 15. So we can see when we jump the first 15, when j is 0, we're up here. When j is 1, we get down to the number 7. These subscripts for you in the Zoom is probably impossible to see. That's why I blew them up over here. 1 and 7. And then the next number is, it hits is a 9. Next number hits is a 3. And then it goes back to its home, which is technically not curly f1, but curly f61. back there. And then it repeats infinitely this 1793, 1793, 1793. What if we shift one tick and start at k equals 2? Then we get the exact same sequence. We see something lurking in the last digits that we wouldn't have seen if we didn't kind of put this on a circle. Like, why is this sequence in particular repeating itself? What if we started at the next tick? We get the even numbers, 2, 4, 8, 6. When we start the next one, we get the same sequence again, the 1793, 1793, but now it's shifted. We get a 3, 1793, 179, but they're in the exact same order. So again, there's a lot of Fibonacci richness that's hidden in the sequence in the last digit, but it's very apparent if you wrap it around a circle. And if we go to the 5s, this is what I was calling the fixed 6 signs, Taurus, Scorpio, etc. That astrology stuff. Then we get all 5s. And if we started at the top, we'd get all 0s, or if we started even here, we'd get all 0s. So there's 4 sequences that appear as we move our square around. Only 4 things appear. A row of 0s, a row of 5s, and that 1793 in some cyclic shift order, and a 2486 in some order, but it's always, it's a 4862 or 8624 or 6248. It stays that way. So open research questions. This is for people in the audience right here. There's a direct connection between these sequences, these subsequences, and the cycles above and the following sequences. If I look at the powers of 0, mod 10, well, 0 to n exponents are still going to remain 0. What about 5? When I look at the last digit, the 5 to the kth power is always just 5s. This is the one that's interesting. When we take 7 to the k, we get our 1793, 1793. When we take our 2 to the k, we get that even sequence. So the open research question I give to everyone in Zoom and everyone in this room is solve this. Me and Dan and Miko had too many problems that we had to solve. So we didn't even think about this, but it's an open research occurrence, research question, and that's fertile ground for whoever's watching. What did we do in particular? We looked at things that we call a quasi-Fibonacci sequence, terms that obey the following relation, like the jth one and the jth plus 1 equals the jth plus 2. For instance, 2 plus 4, if that equaled 6, then we would have a quasi-Fibonacci. We don't. 7 plus 9 is 16. If that was 6, we'd have quasi-Fibonacci. We don't. So these are not quasi-Fibonacci sequences, but we were searching for ones that were. So the research question we answered is that for which R values is this subsequence a quasi-Fibonacci sequence for no matter what starting value we have? Let's give an example. Jump size of 25. We're going to start at k equals 3. And then, so we start at 2. I go 25 units clockwise. And then we're at 1. Jump again. 25 units, I'm at 3. 25 units, I'm at 4. 25 units, 7. And notice 2 plus 1 is 3, 1 plus 3 is 4, 3 plus 4 is 7. Is this going to keep on happening? This is kind of creepy. It is just kind of creepy. What is it about the number 25? Actually, it's going to get even creepier in a second. The same thing. And then finally, after the 11th jump, at the 12th, we go back to our starting point and we get a star polygon. What if we started at different numbers? It suffices if I wanted to start at the 8th number. It's just a shift of the picture we had before. If I want to start at this number, the 8th tick, well, I can just look at starting at the 3rd tick because eventually I get there. The first starting value is k equals 0 to k equals 4. This list gives every single subsequence of 25, no matter what k I start at, because any other k is starting at somewhere here in this list. Like, for instance, if I want to start at k equals 8, that starts right at this point here, the 1 that we saw. So we get these numbers 2, 1, 3, 4, 7, 1, 8, 9, 7 all the time, unless we are at k equals 0 or any multiple of 5, then we get the 0, 5, 5. But even that is quasi-Fibonacci. 0 plus 5 is 5, 5 plus 5 is 10, but last digit, 0, 5 plus 0 is 5, 0 plus 5 is 5. So we have that going on there. But what's especially important is this one in red, because this one in red, all of the other rows have that one. 2, 1, 3, 4. Where does it start here? Here it starts 2, 1, 3, 4. Where does it start at the bottom one? 2, 1, 3, 4. So this thing in red is repeating all the time. Okay. Observation 2, what I just said. If we have the jth one and the j plus first one, we get the j plus second one. So we have that for all 5 of these rows. Hence, observation 1 implies that this thing is a quasi-Fibonacci sequence for every k value. Okay, well, I'm delighted by that. But look at these numbers again. I said it's going to get even creepier. Does anyone notice the elephant in this room? I'm not the elephant. The elephant is this list. Are you paying attention? This is the quiz. This is an oral quiz. Is this special, these numbers? 2, 1, 3, 4. We've got a math department chair sitting nodding ahead, but that's expected. Do we have a non-math person observing something here? Yes, yes, yes. Public health. Thank you, Mel. Edward Luca. This is the Luca sequence. It is not hiding. It is here in the Fibonacci sequence when you jump 25 units. Why is it there? I don't know why, but I definitely prove that it's there. I still don't know why. It's just intriguing how intertwined the Fibonacci sequence and the seemingly arbitrary new sequence that Edward Luca created with just the same thing, to start different starting values of a 2 and a 1. So that is kind of creepy that it's in there and hiding unless you put it around in a circle and jump 25 units. Okay, so our results. If R is congruent to 1 mod 4, that means if R is 1 more than a multiple of 4 and 3 does not divide R, then we have a quasi-Fibonacci sequence. Does 25 satisfy these conditions? Yes, 25 is 1 more than a multiple of 4, because 24 is a multiple of 4 and 25 is 1 more than that, and 3 does not divide 25. So this is our main result one of our main results that we proved. And this is another result that we can also go backwards when a number R is 3 more than a multiple of 4. But let's skip the reverse stuff. The reverse stuff is pretty cool, but there's more to get onto. So our most tantalizing of the sequences are R values. Remember, R is the jump size, like we did at R equals 15 and we did at R equals 25 so far. That yields subsequences that are the most beautiful subsequence. So what is the definition of most beautiful? These are the subsequences of the original Fibonacci sequence, mod 10, which themselves coincide with the parent sequence. Okay, there should be a going on in your head. I hear that. So I just worded it up. Let's look at a jump size of 49 units clockwise. So let's start down here at the bottom. If I go clockwise 49 units, my next stop is here. So since this is a circle of 60 points, instead of going 49 units clockwise, why don't we just go backward 11 units? It's the same thing. So my first jump, going backward 11, I go to 1, then I get another 1, then I get a 2, and then I get a 3. So this is quasi-Fibonacci. Yes, 1 plus 1 is 2, 1 plus 2 is 3. However, if you move further on, we get, when we got the first 10 terms, we have 2, 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13, but that's why we see a 3, 8 plus 3 is 11, that's why we see a 1, 3 plus 1 is 4. This is the Fibonacci sequence. After the 60th jump, we've visited every single tick exactly once. And that's because 49 is relatively prime to 60. So that's not the mystery that we've hit every point, but we've hit every point in the order of the actual sequence starting from the top around here. That is creepy. We're like ping-ponging around here, and we're getting the Fibonacci sequence. And there's 15 other jump sizes that do that, not just 49. 8 of those jump sizes do this, though. Go 0, 1, 9, 2. It goes backwards in reverse. So this is our main result, that if R is congruent to 1 mod 4, so I have to define this thing. These are the U60 is the multiplicative group for units modulo 60, meaning numbers that don't share a factor with the number 60. 49 is such a number. 17 is another number. So if R is 1 more than a multiple of 4, then the subsequence coincides with the original sequence up to some starting value. It'll do that. And if R is congruent to 3 mod 4, it's going to do the backward thing. So what is the starting value? That's a technical thing that we've located using primitive roots and discrete logarithms and yada, 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 fun stuff. So open question. everything we did was in modulo 10. It's natural to ask whether this can be done in other moduli. And our results, which of our results generalize that? So again, that's for you or for my future students. Too many research questions, though, to handle that. Can you and power of and I answer these questions? We can do it. Yes, we can. Remember that guy? Missed that guy. Okay. So project 1 was brought to you by Miko, who's a Leo, myself, who's a Sagittarius, and Dan, who broke the fire thing. He should have been an Aries, but he was born a little afterwards and he hit Taurus. We would have all been fires otherwise. Okay. So project 2, myself, new research student currently here, also applying to get for a PhD program. And my collaborator, external collaborator, who retired in the 80s and has discovered me, and now we've been writing 3 publications, and it's quite fun working with Jürgen. So what's the origins? In the first issue of the Fibonacci Quarterly, there was this problem posed. Every sum of 20 consecutive Fibonacci numbers is divisible by the 10th Fibonacci number. So let's take the first positive 20 Fibonacci numbers, and we add them all up. We get 17,710, and indeed 55 divides that. Fun fact, the rest of that number is a Luca number. Fun fact, but it is. Let's shift to another 20. How about if we start at that one, add them all up? 50, we get 75,020. In fact, 55 divides it. And what's that? It's another Luca number. Creepy, right? But it's happening. And if we do that again, 55 divides this, and that's a Luca number. So that's interesting. The question's obviously true because it's saying, show that this is going to happen. So Dan and I looked at the sequence of numbers, the sequence of things, and what did we observe? We considered the greatest common divisor of this infinite sequence of values. And we observed that 55 not only divides each of these sums, but also seemed to be the greatest divisor that was common to all these sums. So what's special about 55 and what's its connection to 20 consecutive Fibonacci numbers? Well, we consulted a dog named Dr. Wolf, a very clever dog, believes that 10 is half of 20. There will be a quiz on that later. 10 is half of 20. And so when he barked the following conjecture, that the GCD of this infinite sequence of sums is F20 divided by 2, namely F10, the 10th Fibonacci number. So if I look at 20 row of 20 sums, 20 Fibonacci numbers summed up, it's always divisible by F10. So yay. What did we prove in light of the latter? There's nothing special about 20. This holds for all numbers that are divisible by 4. 20 is just one of them. So we proved of k, if the number of numbers we're summing up is divisible by 4, then the GCD of the sum of k consecutive numbers equals the Fibonacci number fk over 2. So that's pretty cool. But that was only tip of the iceberg. We proved so many things, like what if k is a different kind of even number? What about the odd numbers? What if we look at different sequences, summing up Luca numbers? What if we're summing up generalized Fibonacci numbers? We went to town, like basically somehow fit everything in like this 25-page paper, but quite amazing results that really a lot of them, mostly by Dan Geyer solely. He definitely is going to thrive in graduate school. So that leads us to project 2 of 2. So this is our 3 characters. We're going to look at new sequences. I'm not going to really talk barely about these sequences. I'm just going to give results because I know time is moving on. But you might ask, how did I meet research project number 2 collaborator Jürgen? Well, did I meet him in person? Nope, not yet. Did I meet him via Zoom? You don't Zoom. No. Did I meet him via 100 emails exchanged between the two to extend results of the data paper to squares of Fibonacci numbers? Meaning we looked at sums of what happens if we square each one and add them up. And yes, and that led immediately. I've never gotten a publication so quickly, but this man has over 50 publications and way more experience than myself in sequences. But we worked together through, well, it's difficult. There's a major language issue, but mathematics is a language. So we speak that together. So that publication came out in 2022. And so Janee joined us in, and we looked at new sequences. The Pell, the associated Pell, the balancing sequence, the Luca balancing, the co-balancing, and the Luca co-balancing. They're all given by recurrence relations, like the Fibonacci number, take the previous 2 to get the next one. For the Pell, we take to get the current term, you double the previous term and then add that to the previous term. So it's Fibonacci-esque. This one's in blue because it's a non-homogeneous recurrence relation. Won't get into that. So what's some fun facts? The Pell and associated Pell sequences. If I look at Q1 over P1, Q2 over P2, Q3 over P3, those fractions converge and rather quickly to the square root of 2. So those are called the rational convergence. That's one reason of many that people have been interested in the Pell and associated Pell sequence. The balancing sequence, this is a sequence that a lot of people probably are not aware of because it was discovered, invented, researched in 1998. That's its birth. So we call n a balancing number if the sum of the first n-1 numbers equals some sum of numbers, sum, S-O-M-E, sum, S-U-M, of numbers after n. So let's do a visual. This is thanks to my student, Janee. This, by the way, is really hard to code in LaTeX. I rely on my younger students to make something as simple looking as this. But this is a great picture. Thank you, Janee, for watching this. So 6 is a balancing number because the numbers before it add up to 15, and I have some set of numbers after 6 that add up to 15. So co-balancing sequence, unlike the balancing sequence, this one doesn't go up to n. The co-balancing does go up to n. And then, so let's give an example. 14 is a co-balancing number because the sum of the first 14 numbers equals this sum of the numbers after 14. Both sides equal 105. So we have n equals 14 and r equals 6. 6 should be interesting because 6 was a balancing number, and that's no surprise. 6, the co-balancer happens to be a balancing number. So we have this, the co-balancer, which is this one, is a balancing number. And I could show you that easily if we went back to the thing here. So we have a co-balancing number, 14, and its balancer was 6. The next co-balancing number is 84, its balancer is 35. Conversely, a balancing number is 6, as we saw in Janee's first, what's that called? Whatever that thing is called, playground, and its co-balancer was 2. The next co-balancing number is 35, and its co-balancer is 14. So there's a connection between those two rows, and we notice that balancing numbers are infrequent. Are infrequent. Look at how large it gets. 6 was an easy example to put on the board, but balancing numbers are rare. Okay, so what did we do? We looked at adding up a bunch, k consecutive Pells, or k consecutive associated Pells, or k consecutive balancing numbers, or k consecutive co-balancing numbers, or k consecutive Luca co-balancing, or k consecutive Luca balancing. We just went through sound all the sequences. Why did we choose these 6 sequences in particular? Because there's some weird interconnections that the people who created these in 1998, I don't think they saw it, but it's apparent when you look at these sums. So when we add up, say, the first 6 Pell numbers, we get this list of numbers. What's the greatest common divisor of that? Well, look, we have 7 dividing all of them. Incidentally, these numbers are associated Pell numbers. 7 is also an associated Pell number. In fact, it's the 3rd associated Pell number. So if I add up 6 consecutive Pell numbers, they're always divisible by the 3rd associated Pell number. That is quite interesting. It's like we had the same occurrence happening in the Fibonacci setting when an even number was divisible by 4. This is for all even numbers. No, I lied. It's not for all the even numbers. So we have this nice visual braid to show you what the if I add up 1 consecutive, or look at k equals 2, like adding up 2 numbers that are in a row, adding up 3 numbers in a row, 4 numbers in a row, 5 in a row, 6 in a row, 7 in a row. If we notice that the odd ones, the greatest common divisor is 1, meaning they're all relatively prime. None of these, there's no one number greater than 1 that divides all the sums. But when we're in the even case, we get this interesting thing. When k is 2 more than a multiple of 4, for example, when k is 6, we just saw that on the previous page. P6 is Q6 over 2. That's the example I gave earlier. So these are different ways to denote different types of even numbers. And that's what's happening here. At the even numbers, we can see that the sequence of GCDs, it's interesting because this is now a sequence of GCDs. This is the tantalizing part, because we are looking at a sequence of sums, and then we're looking at the GCD, and then we're looking at each of those GCDs as we increase the length of the sums. So we have, this is encapsulating a tantalizing new sequence. It's a sequence of the sums of sequences. So what was our results in the balancing and the Luca balancing? We get this interesting thing. Remember I said curly B was the weird one because it was non-homogeneous? We boil down, if we take 10 consecutive co-balancing numbers, we don't have a closed form for it, but we do know that it will be the greatest common divisor of P10 and the number 10 itself. So that's as good as we can get for that. We're struggling now to find a closed form for this, but this, as we increase K, it's not well behaved and we're not understanding it yet, but we will. We will. I'm sure that we will. And this is the Luca one. Luca balancing and Luca co-balancing ones, and we can see something really interesting here between these drastically different sequences, but they are greatest common divisor, all the sums are the same when we're adding up an odd number of things. So that's why we braided these things together, so we can visually see some similarity of what's happening. Why do all of these sums involve Pell's and associated Pell numbers? And now we're at the end of the talk. Can we find results? Can I square, instead of just adding P1, P2, P2, what about P1 squared plus P2 squared plus P3 squared, like higher values for higher exponents here, m greater than 2. And then also that question I said before, the GCD of SK and K, where the sequence is one of these 6 sequences, can we find a closed form for these? This is currently a project on hold, but I want to know more about that. Can you and Power Band I collaborate on these questions? We can do it. Yes, we can. And that's it. Thank you. These papers are all on my website, but I can push them towards you if you're interested. Question from Mel?
Yeah. Looking at the Luca sequence,
Mm-hmm.
and the Fibonacci sequence in the sense that L0 is 2, L1 is 1.
Yes.
And then it goes on. And it seems that that sort of reversal, starting with 2, going to 1, going to 3, seems rather arbitrary.
It
So
does.
what's the rationale or the beauty versus ugliness of starting with 2 in the Luca sequence, whereas in the Fibonacci sequence, you start out with 0, and then it's a 1, and then it's a 1, then a 2, and a 3, and it progresses. It just seems arbitrary.
Well, I am quite certain that Edward Luca, in his paper that's currently still cited often all the time, that he went through many different sequences, and the one that started with 2 and 1, like it was just uncanny, like how it interconnected with the.
Right.
If you start with other values, actually, we have looked at other values, starting values, and looked for more richness and connections, and that's a whole nother research project on its own. But we didn't see such depth of intimacy between 2 sequences as we did with Luca and Fibonacci. Yeah.
Yeah,
I wish he gave them. His paper is just math. He didn't say why, really.
Okay.
Yeah,
It seems arbitrary.
it does seem arbitrary, but it's, as you can see in the, it's embedded. It was waiting to be discovered in the Fibonacci sequence. It's in there. It's completely in there, and I don't believe any other sequences are in there as intimately connected. You know. Mm-hmm. I mean, I wish I could ask him, and I knew French, and I could be alive back then, but. More questions from anyone in the, sorry, anyone in Zoom?
I don't know what it's like to have a brain that works this way. I'm more of an English person, but I'm just fascinated. It seems like you're always looking for relationships, right? In the numbers kind of. But how, and forgive me if this is a horrible question, but what do you see as the significance of all this? Is there like a real world implication, or is this the real world?
Okay. I love that question. I'm very good at the goal. Sorry, let me repeat the question. Eric, I was really bad at that. The first one. The question was, what is the implications of this, or usefulness or application of this type of pure theoretical research? Well, I asked you a question. What is the purpose of the Mona Lisa? Oh, wait, you never answer a question with a question. Okay, but I love that the purpose of this is beauty. Like that is when I give a talk in math settings, sometimes I get a question from people who know about the Fibonacci stock market, kind of something involving that. And I'm like, I don't know anything about that. That sounds very uninteresting. But if you can somehow make money and by studying a sequence, great. But I just think this is like every time when I saw the Lucas sequence appear in the jump size of 25, I fainted. I mean, I didn't really faint, but I was just like, ah, this is so beautiful. It was just touching. It was just like, why is this here? And I think that is what drives mathematicians, the like needing, discovering something that's already there and like pursuing a way to understand why it is there, you know, because it's waiting to be found. And I just hope people get the joy when they read Dan Miegel aBa paper of saying, oh, the Lucas sequence is just magically here, and this is mathematically why, you know. But also it doesn't really say truthfully why. It just we've proven why it's there, but it's just I can't give it any metaphors in the real world. I'm so stuck in this theoretical world. I'm sure there are metaphors in the real world. You know. And to answer your question, just I love that the application is beauty. You know, makes me feel less like an egghead. Yes, that's why I love teaching Math 104. I have all of these students from Haas, the theater, fine arts, music, and they keep me from being completely square. Any other questions? I wore blue gold today. Just trying to celebrate. Yeah, it's Friday. No, it's not. But every day is Blue Gold Friday. Love our institution. Yes. Anybody else? Okay. Thank you.